Perhaps the most striking and conspicuous feature of the V2 rocket is its shape. Instantly recognizable, elegant, beautiful even, despite its deadly purpose. At the time, so evocative of modernity and the prospect of things to come. Much of the critical technology we see in missiles flying today is the undisputed legacy of the V2. And yet, that unique, super-fast, double-ended tangent ogive shape is one of the masterstrokes least likely to be seen on a modern rocket. Nothing new that resembles a V2 has been seen since the 1950s. And yet, the shape has such a hold on our imaginations that we use it again and again in art and design, in everything from children's toys to business presentations. Type rocket icon into Google, and you're unlikely to see a single Saturn V, Ariane, or Falcon Heavy, just page after page of stylized versions of a shape inspired, distantly but unmistakably, by the V2 missile. People use the image to signal success, speed, and power, and strangest of all, modernity, even though they know little of the origins of this iconic shape from the late 1930s. Where exactly did the V2's beautiful, revolutionary shape come from? And why does it linger in the imaginations of modern visual artists, while missile engineers long ago consigned it to the dustbin of history? Hello again. In this video, I'm going to be looking in some detail at the rather surprising origins of the V2's body shape. The design of an aerodynamically efficient body shape is affected by numerous factors. And as part of the modern missile design team, the aerodynamicist is expected to harmonize these factors in formulating an ideal aerodynamic shape before the flight testing process begins. Germany's 1930s project to develop the world's first long-range ballistic missile lacked the critical research clarity that we take for granted today. This is hardly surprising in the absence of an earlier evolutionary rocket history to draw from. Yet the V2's body shape for this radically new technology was entirely successful, with the main elements changing only slightly in the 7 years from its birth in May 1938 to the end of the war in 1945. Later in this series, we'll delve into the details of the V2 missile's guidance and control system. But the missile's body shape is crucial for stability, serving as the foundation for the control and guidance system. So first, let's make sure we know exactly what shape we're talking about. Now, you've seen me looking at models like this before, and maybe you can see the shape here plainly enough. But the way the fins flare into the body can actually make the shape somewhat difficult to see. So let's just tick it off for a moment. We've got the tangent radius ogive cone section here, which comes back to about here somewhere. And then from there down to here, we've got a parallel section, and then we go into this conic section again. Now, it may not be obvious looking at it like this, but this taper here is identical to the taper at the front here. And that's what I really want to expose to you with the aid of these other models. So first of all, have a look at this miniature version of what we were just looking at and break down the shape so that we can understand it very clearly. First off, I'm going to remove the warhead, which is this top section of the missile. So I'm going to remove that cleanly and just put that down. So now we're left with the body without the warhead. Now this breaks down into three roughly equal length components. We have the tail section, we have the fore section, the front cone with the equipment bays, and we have this parallel midsection. That really is just a plain parallel tube, okay? So this section is drain pipe straight. It's these sections here that have the conic shape to them. So comparing those two, you ought to be able to see that the actual sections here are the same length. So discounting the little bit extra for the fin, you can see that the body shape parts are exactly the same. And if we bring in the central tube, if we discount these little white bits here, which are just to allow me to put the model together, and I offer it up, you can actually see that we've got a equal part again. So it's made of these three elements, and they are all thirds. Incidentally, while I've got the model in pieces, I just want to show you it assembled with just the fore and aft conic sections. There. If I just pop the warhead back on, there it is without the middle parallel tube section. Now if we do a bit of video jiggery pokery, reducing the ogive ratio to say only 3 times the caliber, we end up with a missile shape very like the rocket icons I showed you at the start of this video. Anyway, I digress. So if we put this back together again, these 3 equal parts, we end up with the missile. So that's the first message that you get, is that the missile is made up of essentially 3 equal parts: parallel section, conic section, conic section. Now it's still a bit confusing because we've got the fins in the way. So we've got another model here that I'm going to show you. I'll put this one back together with its warhead. This model needs a bit of unpacking. So first, let's look at this drawing of the A4 showing its final production shape from February 1944. I've taken it into Photoshop so I can show you some overlays. I want you to follow the ogive curve here, blending into a perfect radius tangent at the start of the parallel tube section, and then running into another tangent radius curve here in the tail section, running right down to the thrust ring where the rocket jet exits the missile. So far, we covered a few moments ago. Now let's colorize the core shape red to make it easier to see. I'll just blink that image so you can see how well it fits. This is where things get a little odd. I'm going to flip the shape 180 degrees and show you how well the nose section fits at the tail end. I've just got to nudge it a bit to the right to get the taper on the curves to match up perfectly. I've put some arrows so you can see the body line on the original drawing, and I'll blink the body shape again to see how well it fits. Now let's bring the original coloured body shape back. And now we can see this has created a double-ended curved lozenge shape. You'll see it better when I turn the whole thing white. And now we have this extraordinary double-ended torpedo shape. I'll blink it so you can see the fit. Now this isn't in any sense the actual shape of the V2, of course, but it is the underlying form that the aerodynamics designers had in mind and were trying to approach when thinking about the core body shape of the V2. I'll explain why this double-ended torpedo so enchanted the aerodynamics specialists at Peenemünde a bit later. And with this shape, let's call it the push-me-pull-you shape, I can proceed to baffle you and have the fins or warhead at either end. I could muck you about indefinitely with this and take bets on which end is which, but I have a serious intent here. And that's to bring home to you that there is a form of shape at the core of the V2 that is far from obvious from a first look. A shape that the A4's designers were aiming for. A shape that's hard to appreciate without removing the fins like this. And to give it a name, rather than my push-me-pull-you, the shape is a spherical tangent, radius ogive, double-ended torpedo. So, hopefully that's communicated the proportional dimensions of the V2, this idea of these thirds that it's composed from, plus the warhead. Hopefully that's a memorable image you can carry away. But I also want to explain how we generate these curves. The curve of the tangent radius ogive fore section and the aft section of the missile, where that actually comes from. Let's go back to one of our rather odd shapes here. So how this curve is generated and this curve, what process, how it's related, and how we can be sure that we get the proportions right if we're building a model, for example, of the V2. Let's look at that now. So let's make sure we're absolutely clear about this ogive radius. So the ogive curve is here, and we know we've got another one at the back here, and it's the relationship between the caliber diameter, so this parallel section here, and this radius. So first off, I'm going to measure that with a caliper. Make sure it was on 0 to start with. Just get that in a good position. There you go. Can you see that there? 27.58 measures that pretty good in that position there, showing you the caliber. So 27.58. Now, if we put that into our calculator here, 27.58 times 12.5, hey presto, it comes out at 344 and a little bit left over. So I've created a circle here. You can see it's 688 in diameter, and you can see the radius here of 344 millimeters. Now if I put the missile in position on the curve here, you'll see what a beautiful fit it is for that curve. If I just adjust that a little bit, you should be able to see what a lovely kissing fit that is. There you go. Can you see that? What a good fit that line is to there. And let's just put on that strange push me pull you shape that we were looking at earlier. Let's put him on there as well. And just roll that into position there. Maybe that's even with the white line showing it up that little bit better. You can see how perfectly that falls in and then just drifts away as the parallel section comes around. Okay, so that explains the radius ogive concept of the relationship between the radius of the curve being the circle being specified by multiplying the caliber diameter by a factor of 12.5. If you're wondering where the 12.5 times multiplication comes from, stay tuned. I'll be covering that in a few minutes. But first we need to progress some other fronts. I started this video saying that the distinctive shape of the V2 was instantly recognizable. However, the more subtle aspects of the shape are not so easy to see and understand. Even people who have made it their business to reproduce the V2, at least in miniature, occasionally get it wrong and misunderstand the critical elements of the V2 shape. The box art of this model kit shows a missile purporting to be a V2, and the same with this one. Whatever they are, they're not V2s. Fortunately, the actual models seem to be good and the shape is correct. It's probably just the commercial artist responsible for the box art that got it wrong, but it's easily done. The true shape that underlies the body of the V2 can sometimes be difficult to see depending on lighting, the painting on the V2 that we're looking at, or in the case of this model here, even as I turn this around for you to see, it can be quite difficult to discern exactly what shape the core of the body is relative to the fins and the other distractions from the body paint, for example. It's the way these fins have been flared into the body makes it quite difficult to see this underlying core shape of the body. Even when we get a good view of the missile, glare, shadows and distractions caused by camouflage paint can make the shape difficult to see. Only relatively few historical images give us a perfect shot of the core body shape. The four fixed fin structure, known as the V12 fin pattern, is a dominant part of the overall shape of the V2, and it's the main reason the aft core body shape can be difficult to interpret. Incidentally, the name V12 for the fin pattern stems from the range of prototype fin shapes tested. Each test pattern had a Versuchsmuster, or pattern number, and Versuchsmuster number 12, or V12 for short, was the pattern finally selected for production. Let's put the important issue of the fins to one side for a moment and return to the fundamental question of where the core body shape of the V2 comes from. Now, I'm not going to keep you in suspense. The answer's a bullet, not one from a gun like this. Admittedly, this is a stage prop, but if it was a bullet from a real Walther PPK, the bullet flies at only subsonic speed. The bullet, most often connected with the shape of the V2 missile, was a rifle bullet. Now, lots of books have been written about the history and development of the V2. Read almost any one of them with more than about 200 pages, and sooner or later the author is going to tell you that the core body shape of the V2 is based on the standard German Army rifle bullet. In fact, they may even go as far as defining it as the 7.92mm Patrona Speerpoint Mauser bullet, the ammunition for the standard German Army issue Karabiner 98K infantry rifle. So there you have it. It was based on a rifle bullet. Thanks for watching. See you next time. Hold on a minute. Let's run a sanity check on that statement. For a start, they're not actually talking about the bullet that was on screen earlier. This one is, if I take it apart, you can see that it's flat-bottomed and it flies slower than this one. The one that I've got here has this boat tail, and this is the one that they're talking about. And we can see that the boat tail is extended, giving the bullet more volume and more mass, and we can see that they've used two different radiuses to create this aft end of the boat shape. Hence the name, of course, boat tail. Here's another Mauser 8mm bullet with an even more pronounced boat tail shape. It's solid, tiny, weighs about 10 grams, and is spin stabilized. That's to say, helical rifling in the barrel of the gun forces the bullet to spin round its axis of travel and gyroscopically stabilizes the bullet in flight and stops it tumbling end over end. The bullet flies as a result of a single impulse that ends more or less the moment the bullet exits the barrel, and its speed is at its maximum of about 760 meters per second when it leaves the barrel. That's about twice the speed of sound. But as a result of air resistance or drag and gravity, its high speed starts to decay away with every foot that it flies. The V2 rocket, in comparison, and I'm using this tiny little model to represent it, is complicated. It's full of moving parts and fluids and all kinds of other things going on. It weighs 12.5 tons and stands 46 feet or 14 meters high and is driven by a steady 25 tons of thrust for about 1 minute. At the end of the first second of flight from the launch table, the V2 is only doing about 20 miles or 32 kilometers per hour. At this stage, Usain Bolt and my cat Boswell, admittedly, before he died, could both outrun it on the flat, whereas a bullet, well, you fill in the blanks. So the connection between the bullet and the rocket is not looking so obvious. About the only unforced link you can give them is that they both fly without wings, and at some point they both move very fast, faster than sound. We need to think back to the world of the 1930s that had no examples of supersonic flight from aircraft or rockets. Gunnery's greatest achievement at this time was still the huge Paris gun used by the Germans against France in World War I. It could fling an 8¼ inch or 21 centimetre shell weighing over 234 pounds or 106 kilos, 10% of which was high explosive, about 80 miles or 125 kilometres. The A4, in contrast, was destined to fling a ton of explosives over 160 miles. Despite the striking differences between the spin-stabilized bullet and the fin-stabilized rocket, the outstanding success of the science of ballistics made the bullet shape a sensible starting point for the new rocketry technology. After all, the Mauser bullet had more than proved itself with billions of successful launches during the First World War. I want to take a few moments to highlight the crucial role in early German rocketry of a standard ballistics reference work and one of its authors. This book, the Handbook of External Ballistics, deals with everything that occurs on the trajectory of the bullet or shell from the moment it leaves the muzzle of the cannon or gun to the point where it arrives with the target. No work in the 20th century probably did more to further the science of ballistics than Krantz and Becker's Handbook of External Ballistics. Originally written and compiled by Dr. Karl Julius Krantz of the Technical Military Academy at Berlin-Charlottenburg, the text was later revised and extended by his student and collaborator, Captain Karl Emil Becker, and published in 4 volumes between 1910 and 1926. The edition I have here was published in 1921, and the table of contents reads like a recipe book for the early needs of Germany's fledgling rocket team. The Handbook of Ballistics had its most significant influence during the period between the world wars, none more so than on the leaders of Germany's project to develop the large liquid-fueled long-range rocket. Almost everything we see in the ballistics-related shape of the A3 and the A5 comes from this book. And this is hardly surprising, because basically almost anything to do with the science of ballistics can be found in this book. Well into the 1930s, this book was one of the most commonly cited in the reference lists of virtually every academic paper concerned with the aerodynamics of high-speed projectiles. The handbook frequently referenced the limited state of knowledge regarding bodies travelling at inordinately high velocities. For the fledgling rocketeers at Kummersdorf and Peenemünde, this outspoken skepticism of existing ideas about the ideal projectile body shape was one of the most liberating aspects of the work, especially when other, seemingly authoritative ballistic experts in Germany were advising the rocketeers of the outright impossibility of fin-stabilized supersonic rockets. This and Becker's steady mentoring to the leadership of the rocket project in the fledgling stages of its development was an important element in its early successes. The core body shape of the A3, A5 and A4 certainly has its roots in the 1914 Speerpoint Mauser rifle bullet. However, the 1921 Handbook of Ballistics reveals why the rocket series nose cones have a more slender and pointed tangent ogive than the 7.92mm rifle bullet. On page 73 of the book, we find a discussion of a rule of thumb proposed in a 1908 paper by the German ballistician Willy Heidenreich. Based on practical experiments, he observed that doubling the ogive radius reduced the drag of a projectile by between 14 and 19%. I'm just measuring this 7.92 or 8mm Mauser round. It's coming up at about 7.9mm, so that's what I'll use. I'll put it back here. Got a little model of an A4 or V2 here, and I'll take a snapshot with my iPad. I'm using an app called Partometer that will, after I've calibrated the photo, let me make measurements directly from the image. In particular, the radius dimensions of the bullet and the rocket model nose ogives. I've calibrated the picture, and a measurement of the caliber or maximum diameter of the top boat tail bullet is measuring up at 7.89mm, which is pretty close. I've already lined up the radius tool with the sharpest outline of the bullet ogive, and I'm getting 59.4mm and some change. The line's a pretty good fit. Let's put that into our calculator. 59.43. That last digit should have been an 8, not a 3. We're only interested in the first 2 digits, so that won't affect the result. Divided by the caliber of 7.9mm, and we get 7.5 as the number of times we need to multiply the caliber diameter to get the ogive tangent radius. Write that in so as not to forget it. Mauser 7.5. Now let's move the sample points down and measure the caliber. That's the drainpipe straight section of the A4 rocket body. Feel free to talk amongst yourselves while I do this. Comes up as 20mm, which is correct. Do the same for the radius plot points. Bit fiddly. Still a gap showing there. Zoom in a bit. Help if I had it in edit mode. That's better. Nice and snug. The radius is measuring up at 254 millimeters. Once again into the calculator. 254 divide by 20. The answer is 12.7 times. Not perfect. The correct answer should be 12.5, but close enough for government work. So we'll put the correct ogive radius multiplier down for the record. The A4 or V2 requires the caliber to be multiplied 12.5 times to specify the ogive radius dimension. So, all things being equal, and referring to Heidenreich's admittedly approximate rule of thumb, the ratio of caliber to radius employed on the aggregate series, the A3, A5 and A4, has about 11% less drag than if the lower ogive ratio of the Mauser bullet was being used. This graph, from the website of the late Lutz Moeller, shows the relationship between the caliber labelled D and the ogive radius R, and relates the shape to the anticipated velocity in meters per second. We can see clearly how the shape changes as we move from an ogive radius of 10 caliber diameters to an increasingly slender and longer ogive of 15 diameters. This idea, drawn from the body of ballistic knowledge of the 1920s, is typical of the valuable input provided to the von Braun Rocketeers, sometimes directly, by Carl Becker, and through him, the wisdom of his old boss, Karl Kranz. So as vital and modern as the German rocket work appears to be in the early part of the 1930s, we've now got part of our answer, at least, about where these issues of the shape, especially as they pertain to the A3 and the A5, the Spitzgeschoss, the pointed bullet, how that plays into the tangent radius ogive of the A3 and the A5, and eventually ends up on the A4, of course, and the boat tail shape from the aft end of the bullet in use on the A3 and the A5, and then of course available for subject to change on the A4 later on. So that's definitely part of the answer about where the shape comes from. It's from the ballistic knowledge of the 1920s. Although much of the book's material reached back to the previous century, Kranz and Becker's landmark work had the most influence on the new breed of aerodynamicists working in the early 1930s. Theorists and practical experimenters like Theodor von Karman, who, with others, was working steadily in the developing science of supersonic aerodynamics. Before we move on, an interesting thing to note in this book is on page 82. In a chapter entitled On Air Resistance, there's a discussion regarding the calculations of the most drag-efficient shape of a shell. It finishes with a group of illustrations, and it's the bottom two that are most interesting. The authors describe shapes 4 and 5 as potentially ideal. They note that the shapes have been discussed by ballisticians since at least 1744, saying that the torpedo form is useful on purely hydrodynamical principles, but the need for the stability of the shell in the bore and in flight, in the air, and other practical reasons are opposed to this form of shell. Now don't bother with the details, just remember this shape and the fact that this book was published in 1921. That Kranz and Becker discussed this shape left it as an intriguing open question for later investigators. Regardless of its inappropriateness for use with gun barrels, it might be an ideal low-drag shape in situations where the objections relating to gun barrels would not apply, like rocket-propelled projectiles perhaps. It was a small hint that later investigators noted, and more than one ran with it. Before we move on, I want to consolidate some of these ideas and anchor them in time by looking at some blueprints that tie the A3, A5 and A4 missiles together in what I think of as the early ballistics-inspired era of their development. Let's start with this drawing of the A3 from January 1936. Just take in the overall body shape and these dimensions. the boat tail radius of 2000 millimeters or 2 meters, and the nose ogive radius of 8.37 meters. If we now look at this Peenemünde drawing of the A5 core body shape from July 1938, note the ogive and boat tail dimensions again, 8.37 meters and 2 meters respectively. Don't bother with anything else. I'm just going to put a box around the body and copy it quickly, and then paste it vertically into that A3 drawing I showed you a moment ago. And if I drag it over, you can see it's a perfect fit with the A5 body. I'll just blink the image so that you can see that clearly. If I zoom in, you can see the dimensions of the caliber showing that the A3 was supposedly 0.6 of a millimeter smaller. Make of that what you will. Other than the identical size of the A3 and A5 body shape, I wanted you to see the ballistic geometry of the identical tangent radius ogive nose cones and, more significantly, the identical boat tail aft shape of both missiles, even though they have radically different fin structures. The A5, of course, had a long career through the war as a test bed for the A4, and this April 1942 Peenemünde drawing shows the details of the checkerboard paint pattern used on some A5s. But all I want you to see here is the way the aft boat tail looks when it's combined with the fin pattern of the A5. Now, we'll just take that July 1938 body shape drawing we were looking at and take it into Photoshop so that I can get into your memory with this bullet shape theme. I'm going to get rid of that parallel-sided tube section of the body by clipping out the boat tail aft section and sliding it forward. The bullet shape is already unmistakable. At the top here is an A3 concept drawing from Kummersdorf in 1935. This is just to show you how strong and uncompromised the Mauser bullet analog notion was at the start of the project. You can see the spire point is a good fit, and also the boat tail is a good fit with the flyable A5 over 3 years later. Now let's drop the drawing of the Mauser 7.92mm round below the A5 and slide it up. We can see a good match at the sharp end. The boat tail isn't as strong on the bullet as it is on the A3, A5, but it's worth remembering as a ballistic concept, the boat tail varies with the uses of the projectile. The rounds we were looking at earlier all had differing aft shapes. I want you to remember the abstract idea of the boat shape more than the exact origin of the shape. Now let's round this off with a look at one of the earliest drawings of the A4 or V2 from June 1937. It shows the same ballistics-inspired body shape as the A3 and A5 bodies and defines the core body shape with 3 radii. Nose radius 20 meters, rear section cone radius 27.5 meters, final boat tail radius 2 meters. Note that the caliber of 1.6 meters multiplied by the caliber to ogive radius number of 12.5 gives us the 20 meter tangent radius of the nose. Now the point of all this is to help define, even if somewhat vaguely, the ballistic era for the general mentality of German missile development, so that later we can detect a definite end of the ballistics era in the early months of 1938, when ideas stemming from more recent research in the growing science of supersonic flow began to influence the missile body design decisions being made in Peenemünde. The story of the A4's body shape starts in earnest in the dying days of 1935 with the first designs of the A3. The A3 was proposed as a prototype for the full-sized A4 missile, later known as the V2. It had an engine that delivered 1.5 tons of thrust and, fully fueled, weighed around 1,630 pounds or 750 kilos. On January the 6th, 1936, Wernher von Braun presented the latest design of the A3 to experts at the Aachen Aerodynamics Institute in Germany to investigate its stability. The work of testing the A3 was given to Dr. Rudolf Hermann, and in July of the same year, after testing model shapes in the small 10-centimeter Aachen wind tunnel, he established that the existing design was unstable. Dr. Hermann went on to propose changes to the fin design and their positioning to make the A3 missile stable in flight. His changes centered entirely on the fin position and size. Importantly, he made no changes to the proposed ballistics-inspired core body shape. And here is the late Dr. Herman explaining the nature of an aerodynamically stable projectile with the aid of a ballpoint pen.
This is my little missile. And here you can think the fins on. And when the air, when it's flying like this, the airstream comes like this. It has three types of forces. One, the drag, which is in the direction of flight, it retards it. Then, in the moment when it has angle of attack, it has also lift, which carries up and down. Very important, otherwise you could never have turned the A4 in a circle in order to go wherever you want to go. And then the fins here are very important in order to stabilize it, because they must produce a force here that when it's flying like this and goes up with the nose, a force here on the tail puts it back to zero. So always when it tries to get away from its flight, it is automatically brought back to the flight. You call this stable, but particular aerodynamically stable, because it's the aircraft which produces.
The von Braun team had 4 A3 missiles to launch. The guy with the feather in his hat is von Braun. All 4 test missiles took the line of least resistance, heading into the wind and crashing into the sea. Only one of the 4 managed to fly beyond 350 feet altitude. The missile was found to be stable, but too stable for the underpowered control system to counteract the steady 17 miles per hour wind prevailing at the time of the launches. Calculations showed that the control system of the A3 was so underpowered that the missile was unable to withstand crosswinds of even 8 miles per hour. It was a crushing failure, but at no point was the bullet body shape of the A3 in any way implicated as a contributing factor in the cause of the failure. Further discussions between von Braun and Dr. Herman concerning the difficulties of accurately testing small models in the tiny 10-centimeter tunnel at Aachen led to discussions about the possibility of building a much larger and more powerful wind tunnel with a large 40 by 40 centimeter test section. The decision to build a large, well-resourced supersonic wind tunnel system in Peenemünde followed soon after. Work on the Peenemünde wind tunnels began in early 1937. By April the same year, Dr. Herman was installed as director of the Peenemünde Aerodynamics Institute with an initial staff of 20. The facility would become the most sophisticated and powerful wind tunnel system in the world at that time. Today, finding what remains of the Peenemünde Aerodynamics Institute requires some effort. It's hidden amongst the trees, amongst the rubble of the rest of the Army Research Centre. It's behind fences and locked gates. There are no signs to commemorate what was here, or its significance. If I overlay a historical reconnaissance photo from 1943, things look a bit clearer. And here is the Aerodynamics Institute, located on the main road through what looks more like a small town than just a few army buildings. If I overlay this image by researcher and photographer Martin Troller, we can see which parts of the building house key pieces of equipment. The pumps are in the left wing, the vacuum vessel is in the central hall, and the wind tunnels are in the right wing, with the special air drying filters at the extreme right-hand end of the building. Entering the site from where the entrance hall once stood, we find the lower level or basement that held the giant 1,000 cubic meter steel vacuum sphere. There are a few rusting cleats and brackets on the walls, and here and there a few stout I-beams, vestiges of the momentous things that once happened here. Rudolf Herman and his deputy Hermann Kurzweg must have stood here many times, and many of the other famous names of rocket development. To the left there, we can see the large cutouts in the adjoining foundations to accommodate the air extraction pipes that passed from the vacuum pumps to the great sphere. There's still some white paint on the shattered walls to remind us that we're standing inside what was once a building and a place of intense human activity. Here we get a better shot of the gullies in the floor that carry those pipes from the vacuum sphere in the centre to the pump room, which is now on the right in this view. We're in the right-hand wing of the building now. The leaf litter and the moss look normal enough until I scrape a patch away with my boot and find that the forest floor is made of thick concrete and once supported the wind tunnels. If you're into rotting tree fungus, this is a good place. We have a tile here still attached to the concrete floor. Booby traps, like this concrete reinforcing rebar, are well hidden amongst the leaves. If you need a reminder that this was a place where people worked, just outside the walls there's another trap, an inspection point for the sewage and wastewater network. You can just see the central north-south road at the top of your picture. So this is all that remains in Peenemünde of what was once the world's most powerful and sophisticated supersonic research facility. But if we were here in, say, 1939, 1940, we would see something very different. If we simulate a Google Street View and drop down into the road outside the Institute, we find ourselves outside a large brick building. The high central hall housed the huge 1,000 cubic metre vacuum vessel made of double riveted steel sections. That rail you can see a little above the middle actually runs around the entire equator of the sphere and carried a rolling ladder that could be used to inspect the entire vessel. The ground level windows running along the whole front of the building are offices and workshops. The large wing to the left houses the 3 pairs of rotary vacuum pumps driven by 3 equally large 270 kilowatt electric motors. They could be operated in series or parallel depending on the level of vacuum required. The right wing housed the wind tunnels, which were of the blowdown type that relied on a hard vacuum in the central sphere and then opening a fast-acting valve that allowed the air to rush back into the sphere through the test section of the tunnels. At speeds involving supersonic flow, accurate measurements required that virtually all moisture be removed from the air used in the test. The air expands through the nozzle in the test section, attaining low pressures and temperatures, with the risk that if humid air was allowed to enter the test section, it might condense and form clouds. 2 walls of silica gel filters, 13 foot or 4 meters high, and powerful 600 kilowatt heaters to dry the filters were used to ensure that only dry air entered the tunnel. Just before the test section, a honeycomb system ensured the airflow was a smooth, parallel jet. The operation of the system required a special, fast-acting valve on the wind tunnel. Speed was of the essence, as test runs at the highest Mach numbers could run for a maximum of about 25 seconds. Initially, this valve would be closed, and the evacuation valve would be opened, allowing the pump system to extract the air and create a powerful vacuum in the sphere. This took around a minute. When a sufficient vacuum had been achieved for the flow velocity required for the test, the pump valve would be closed. The vacuum would be held steady in the sphere until the test section was ready, and the run could start with the opening of the fast-acting valve. Air would now rush through the tunnel, allowing measurements to be made as the sphere once again filled with fast-flowing dry air. A point would be reached where the velocity could no longer be maintained by the reduced vacuum, and the fast-acting valve would close, ending the test run. The process would then start again, ready for the next test run. Here we see the 40 by 40 centimetre wind tunnel not long after its completion in 1939. The remote control console, shown here on the left, was later moved to leave the central area clear for the increasing number of personnel the test area needed to accommodate. The test section had thick glass sliding doors on both sides that allowed easy access for models and support rigs to be changed quickly. The Schlieren imaging apparatus, manufactured by Carl Zeiss, could be lifted on and off the tunnels by this eye using the overhead crane. The apparatus was on rails and was positioned over the test section as needed. An operator could then make Schlieren observations or record film footage and photographs from the display screen. By 1940, After the wind tunnel was through its shakedown period, it was producing a rich and constant stream of unique supersonic flow data that was answering crucial questions about the performance of the A4 missile and dictating the direction to be taken by some of the open design issues. But almost all of this important work was focused on the fin complex and the exhaust jet, how the jet flame affected the drag, the expansion of the jet flame with altitude, as well as many questions relating to the control moment of the jet vanes and the aerodynamic fins. That's to say, practically no time was spent looking at the core body shape. And on the very few occasions that it was looked at, it was mostly to confirm that it was causing no problems and did no harm to the trajectory of the missile. This later picture of the wind tunnel gives us another shot of the 10-meter long Schlieren apparatus, this time demounted from the tunnel. There's the remote control console again, located in its later position on a more extensive control stage. In this view, we can see that as time went on, the research division developed more advanced ways of measuring what was going on at the surface and boundary layers of the models under test. We see teams of observers and recorders. The observers are standing at the display panels on the manometer station, and their recorders are seated immediately behind them. The 12 manometers are connected to the model with these thin air pipes. Each panel has up to 10 tube manometers, each requiring a separate thin pipe connected to some point on the model. The wind tunnel model we see here has 12 thin pipes that open at various points on the surface of the model, but the number of sample points is limited by the number of pipes that can be connected through the sting point here. Here we see a different design with more sample connections, but at the expense of a more intrusive mount. Finally, they came up with a way to connect up to 120 pipes to sample points by halving the model and mounting it on a plate. The effects of the plate could be deleted from the measurement data without reducing the accuracy of the data. Now again, if you read almost any good book about the development of the V2, and the vital contribution made by the Peenemünde wind tunnels will be prominently featured. And it's completely correct. The vast amount of wind tunnel work carried out by Dr. Hermann and his colleagues was crucial to the success of the A4 V2 missile. But here comes the catch. Contrary to the weight of this popular opinion, the wind tunnel work did not define the shape of the entire missile, and certainly not the core body shape. Over 30 people worked in this space, working in shifts virtually round the clock. The volume of work generated was staggering, and all without digital computers. And yet, we come back to this same strange omission. Practically nothing can be found in the boxes and boxes of documents generated by this work that looked with any detail at the core body shape. This one picture gives us a clue to understanding this strange omission. Clearly visible amongst the lineup of aluminium wind tunnel models, we see an odd man out. A strange little model that would turn out to be made of wood, with a different shape to the A5 and with fins made of some dark material that bizarrely turned out to be rubber. Here's a better picture of the same model. And the most important points to note is that the simple shallow radius curve easily visible against the fins is the same as the curve on the nose cone. And the date written on the model, May 1938. And here is Hermann H. Kurzweg, the man that made this model. We see him in the centre here in 1952, showing rather starry-eyed SDS students a German A4B model in the ex-Peenemünde wind tunnel at the White Oak Naval Ordnance Laboratory. He became Associate Technical Director of the Aerodynamics Lab in 1956. But during World War II, he was the head of the Research Division and Deputy Director of the Peenemünde Aerodynamics Institute. In May 1938, the Peenemünde wind tunnels were still not ready, but the design team were desperate to move forward and were clamouring for a basic tail fin and body shape for the new A4. Hermann Kurzweg, at that time Deputy Director of the Institute and Director of the Research Division, was given the job of determining this shape. And this is where our story gets a bit surprising and rather funny. He makes this model. Hermann Kurzweg left a precise account of how he made and used this model in a memoir published in 1957, The History of German Guided Missiles Development. The book, edited by Bernecke and Quick, gave a number of key Peenemünde scientists an opportunity to tell the story of their personal contribution to the development of the V2. Kurzweg contributed Chapter 5, entitled Aerodynamic Development of the V2, which clarified the role of the model at a critical moment in the V2's development history, as well as the literature available at the time that influenced his thinking. This is a replica of his model. He says he carved the body from a piece of Peenemünde pine in the space of a weekend. He said he made these fins out of a bit of surplus rubber. He put a brass plug into the body to be able to control the center of gravity. And although he copied the safe, established ballistic shape used for the A3 down to here, for the tail, he adopted principles he had gleaned from Theodor von Karman and Norton B. Moore's landmark paper of 1932. The two radiuses used on the boat tail were eliminated in favor of a straight repeat of the slender tangent radius ogive used at the front. Kurzweg carried out the first test using the model by throwing it into the wind from the second story of his house. So that explains why the rubber was chosen for the fins, in the hope that they'd survive the indignity of being flung off the roof. Now, all this would not seem so amusing until you reflect that just down the road, his boss Rudolf Hermann is in the late stages of finishing the world's most sophisticated wind tunnel, going 3 times over budget and costing an estimated million Reichsmarks. Meanwhile, teams of engineers, quivering like whippets, perched at their drawing boards, clutching their slide rules with bated breath, waiting for the word from the second in command at the Aerodynamics Institute, no less, on the new shape that would define the A4 missile. And here's Hermann's trusted deputy throwing a wooden rocket off the roof. When you think of what's coming, this is an incredible moment in the development story of the V2. In fact, Hermann Kurzweg was a very competent researcher, and he quickly realized that the thrown trajectory of the model didn't last long enough to reveal what he needed to test for. The short trajectory didn't allow the aerodynamic moment to overcome the inertial moment of the thrown model. So he switched to suspending the model on a wire attached to the roof of a car and had someone drive him along a straight road at 60 miles per hour, observing the oscillations and testing 3 different fin shapes. Still pretty basic stuff compared with what went on in the wind tunnel later, but astutely observed and just good enough to allow Kurzweg to present the design team with a reliable body shape and fin complex design that allowed them to press ahead with the most urgent design details. And most incredibly of all, I think, and it speaks volumes for the competence of the aerodynamics team and Hermann Kurzweg in particular, this is essentially the final shape of the V2 and how it still looked at the end of the war in 1945. And here it is in May 1938. There's some small changes with the size and angles of the leading and trailing edges of the fins, but if it was cheese, you couldn't live long on the difference. I want to just take a moment to look at that academic paper mentioned in Kurzweg's memoir. Like the Handbook of Ballistics, this seminal paper had a significant role in the story of the evolution of the V2's core body shape. Authored by Theodor von Karman and Norton B. Moore from the California Institute of Technology, Pasadena, the paper had a noteworthy influence on the aerodynamic research conducted at Peenemünde. Von Karman was born into a Jewish family in Budapest, Hungary. Living and working in Germany, he witnessed the rise of the Nazis, and by 1930, von Karman accepted the directorship of the Guggenheim Aeronautical Laboratory at Caltech. Later, he became a US citizen. First presented in 1932, the paper, entitled Resistance of Slender Bodies Moving with Supersonic Velocities with Special Reference to Projectiles, was the result of von Karman's observational experience with wind tunnel experiments dating back to before the First World War and his time as Director of Aerodynamics at the University of Aachen, Germany. Norton Moore's contribution as junior author was largely condensing the data into concise hydrodynamic mathematical formulas. The paper discussed calculating the resistance experienced by objects moving through air at speeds faster than the speed of sound. While previous research has focused on two-dimensional supersonic flow problems, there have only been limited attempts to solve the hydrodynamical equations for three-dimensional cases. The paper was groundbreaking, as it was the first to propose a formula for determining the ideal proportions of a low-drag, slender-bodied shape based on mathematical principles. The study looked at slender bodies of rotation, or shapes that can be created by rotating a profile, such as bullets or projectiles without fins, and successfully developed a methodology for assessing the pressure distribution on the supersonic projectile, enabling the prediction of the drag effects of the shape. The authors derived fundamental equations that revealed universal characteristics of slender projectile behavior. Their results aligned closely with values obtained from ballistic experiments. And although the authors used data from observations of the performance of the German S or Speyer point Mauser bullet in their calculations, and the paper had several references to Krantz and Becker's Handbook of Ballistics, even reprinting one of Krantz's original high-speed flash photos, the work gained significant interest from investigators at Peenemünde precisely because its mathematical formulas could be more broadly applied to supersonic projectiles beyond just the realm of bullets and artillery shells. Although steeped in historical ballistic data, von Karman and Moore's work was an important theoretical step, essentially forming the first chapter or cookbook of the growing science of supersonic missile aerodynamics. Now, I say cookbook because their mathematical models were not entirely precise. Von Karman himself acknowledged that his and Moore's treatment was just a beginning, demonstrating good agreement with some experimental results, but that further research and experimentation would be necessary to refine the formulas for greater accuracy. In fact, somewhat to von Karman's annoyance, another German researcher just a few years later, Wolfgang Haak, analyzed just the mathematical formulas in von Karman and Moore's work and spotted what was truly universal in their calculations. Haak used his expertise in differential geometry to uncover what they had overlooked, without reference to any new experimental data. Haak built upon von Karman and Moore's approximate formulas from the 1932 paper to develop an optimization method for projectile shapes. He focused on minimizing wave drag by calculating the most efficient shapes for given calibers, lengths, and volumes. The result was the Haak minimum drag shape could now be specified from any two of the three variables, caliber, length, and volume. This eliminates the need for variations of simple geometric forms to specify the tangent radius ogive as used on the V2. From Wolfgang Haak's perspective, the high-velocity bullet was successful only insofar as it approximated the ideal aerodynamic shape. After von Karman, Haak's rigorous mathematical description of supersonic flow could now be applied to prescribe aerodynamic shapes without reference to these historical approximations. And here's a model of that Wolfgang Haak shape, that minimum drag, minimum air resistance body, looking not unlike the finless A4 that we were looking at earlier, this time composed not of radiuses and sections of circles, but curves dictated by the mathematics of supersonic fluid dynamics. Where others had described the results of supersonic flow experiments and the effects on various existing body shape, Haak's incisive step had been to derive a prescription for the ideal low-drag shape by essentially boiling down the particular mathematical conclusions of others into a generalized account of the statistics of the ideal minimum drag shape. Remember this from the Handbook of Ballistics? The perfect low-drag shape has finally come of age 20 years later. Wolfgang Haak presented his milestone paper to an audience of aerodynamicists and other experts at the Peenemünde Army Research Center in October 1941. Wernher von Braun was in the audience. It's important to remember that Hark's paper was published a full year before the V2's first successful flight in early October 1942. Although Hark's top-secret paper didn't directly influence the subsequent body shape of the V2, his rigorous mathematical analysis confirmed and extended von Karman's work. This provided some much-needed vindication for the general character of the body shape finalized by Peenemunder's Aerodynamics Institute years earlier. In the face of the uncertainties and lack of endorsement from many of Germany's leading ballisticians, Hark's work must have been a welcome vindication of the ideas and choices of some of those sitting in the audience. Incidentally, if you're wondering why I haven't referred to this shape by its more well-known name as the Sears-Hark body, it's because the American William Sears didn't make his contribution to Hark's foundational work until 10 years later in the early 1950s. Now, to be sure, there's more to missile shape than just the external performance. The outer body form of the missile also defines and to some degree restricts the development of the internal structure of the missile as well. It's difficult to miss the self-evident success of the V2's aerodynamically stable shape. It usually arrived at the approximate location of its target, after all. We noted earlier the weak wind tunnel optimization of the shape, which asked only if the shape did any harm to the missile's flight. Virtually no attempt was made to find a simpler to manufacture design that retained the aerodynamic properties needed by the V2. The elegant-looking double ogive torpedo shape with its tapering internal cavities remained a curse in the area of manufacturing, assembly and revision of the V2 throughout the war. The complexity of the shape made almost every manufacturing and assembly step that much more complicated. Even relatively simple manufacturing actions, like semi-automating the spot welding of seams, are more challenging if the components and the welding frame have to be precisely curved and matched. In contrast, missiles that are drainpipe straight, like this, are just physically easier to construct when so many repeat components are used in these parallel tube structures. It makes revising significant parts of the missile, maybe extending the range with larger propellant tanks, much more straightforward, speedier and more cost-effective. The V2's revolutionary and beautiful shape didn't last long. In just a few years, the double-ended tangent radius ogive was no more. With the A4's designer's initial ballistics mindset, its curved shape had seemed crucial. However, by 1943, with the lessons learned from flight trials and the steady improvements to supersonic aerodynamic theory, it was increasingly obvious that this elaborate shape did not significantly enhance the missile's performance. In fact, other, simpler shapes could have performed just as well, and the advantages of easier construction and assembly for straighter body designs outweighed the minimal benefits of the original shape. By the end of the war, the aerodynamic specialists who had designed the V2 shape knew they would never use the shape again. After 1945, the V2 was copied more or less bolt for bolt by the Soviet Union and named the R1, and was the first ballistic missile weapon system deployed by the Soviet military in 1950, and they left the shape intact. It's worth noting the Soviets subsequently passed the technology to their friends, the Chinese, who called it the Dongfeng 1, or East Wind 1, and they kept it flying until the early 1960s, still with the shape unchanged. But by 1950, one of the R1's replacements was already at the planning stage, and the Scud A, versions of which are still in use today, appeared in 1951 with no sign of the elegant curves of the V2. The missile was a simplified version of the V2 and was easier to make, and the core body shape was drainpipe straight. And so too for the German team led by von Braun working in America. Their first major contribution to US rocketry was the PGM-11, better known as the Redstone. Once again, the body was mostly drainpipe straight with not a curve in sight. As advancements in guidance and control technology occurred, the large stabilizing fins seen on the V2 missile also became smaller and less critical over time. So we're getting a clearer picture of the origins of the A4's core body shape, with its earliest beginnings with the A3, drawing by necessity on the certainties of early 20th century ballistics. The early 1930s saw important developments in the growing realm of supersonic flow dynamics, with the first mathematical theory to predict the wave drag for slender bodies in supersonic flow by von Karman and Moore. By 1938, these ideas were integrated into the design philosophy of the A4's core body shape by Hermann Kurzweg and others at the Peenemünde Aerodynamics Institute. Such a short, sharp shopping list narrative leaves a lot of people and their contributions unrecognized. But Wolfgang Hack's mathematical treatment of the ideal aerodynamic shapes signals that by the mid-1940s, Germany's researchers had developed an increasingly profound understanding of supersonic missile aerodynamics, and all in just a few intense years. The German Rocketeers were not the first to draw guidance and inspiration from the world of ballistics. George Méliès's 1902 silent classic, Voyage to the Moon, drew on the earlier science fiction novels of Jules Verne and H.G. Wells and showed a huge artillery shell being used, somewhat implausibly, in a manned trip to the moon, creating the world's first science fiction film. Many imaginary space adventures would follow. We can use the imagery of science fiction history as a barometer to track artistic inspiration and public perception. Unlike the shapes of our modern motor cars, made bland and uniform by the tyranny of the wind tunnel, we certainly see little sign of the wind tunnel in our current era's depiction of space exploration. Before World War II, the inspiration for the spaceships of tomorrow stemmed from airships and submarines, with at least one earlier notable exception, where artillery projectiles were the decidedly unsafe inspiration for a space program. Jules Verne's evocation of an early NASA and the unforgettable Baltimore Gun Club in his inspirational From the Earth to the Moon of 1865. From the late 1940s and all through the 1950s, books like this one, The Conquest of Space, published in 1949 and written by Willy Ley, one of the best and most well-informed space writers of the era, and illustrated by the great space artist Chesley Bonestell, greatly broadened the appreciation of the prospects of space travel, and at the same time burnt the legacy shape of the V2 into the public and artistic consciousness. Throughout the 1950s, there could be little doubt about what was inspiring artists and driving public perceptions about modern space vehicle shape. Again and again, the V2 missile's elegant body shape, that sleek and beautiful double-ended radius ogive torpedo, was taken as the shape of tomorrow. If one more example from science fiction of an enduring use of the V2 missile shape is needed, the Hugos, long regarded as the world's premier award for achievement in science fiction, adopted a romanticized four-finned rocket ship as both its organization's logo and its physical silver award trophy. The award modeled slender stylizing of a romantic 1950s spaceship can't disguise the historical continuity of this image as earthed all the way back to the wartime V2 missile. Soon enough, the lessons learned late in Peenemünde and post-war wind tunnel research began to be reflected in missile body shape. But only in the early 1960s did this start to influence perceptions in the way artists and the public began to see the V2 shape as seen in science fiction as a bit old-fashioned or romantic. Science fiction and fantasy have their own evolutionary forces, but in the parallel world of the internet, the V2, or at least its ghost, in the form of the tangent radius ogive double-ended torpedo shape, is still flying on millions of pages. Where would PowerPoint and internet marketeers be without a V2 rocket icon to signal rocketing sales? A boom in every sense. I had a good laugh searching for some of these. And your bitcoins were doing so well until they put them on a crypto V2. Now they really are in bits. And you're not doing anywhere near as well as you think, buddy. And there go your savings, strapped to a, oh, you guessed it. But a million websites can't be wrong. Too many to illustrate will carry you back to the top of the page on the back of a familiar rocket icon. And search Google for a new company logo with a rocket and you'll get not thousands but hundreds of thousands of chubby double tangent ogive rockets on your screen. And the Saturn V and the Falcon Heavy barely get a look in. Rocket designers may have abandoned the V2 shape, but artists, communicators and marketeers love the vibe and romance of the 1950s space adventure rockets. And hiding in them all, in plain sight, is that sinister 1940s robot bomb, the first spaceship of the 20th century, the V2 missile. We're not to be blamed. No one is reaching back knowingly to the infamous V2 rocket. These images and icons reach only as far as the optimistic space adventures of the 1950s and early 60s. It's that good iconography that's become so rooted in our minds. But even so, there's no escaping the fact that this imagery was inspired by the wartime V2 rocket. As is so often the way with these things, now that I've encouraged you to recognize the distinctive tangent radius ogive double-ended torpedo shape as the DNA of the V2 missile, you'll start seeing it everywhere. Really, everywhere. So when you're about to download your latest version of Grand Theft Candy Bubbles or the app controller for your beard or bikini line trimmer, spare a thought for that tiny rocket icon at the bottom of your screen. And remember to say hello to Theodor von Karman and Hermann H. Kurzweg. Just some final points before we close. If you're watching on YouTube, you'll find a literature and citations list in the notes under the video, or you can visit our website for further information. And please consider becoming a Patreon member. It gives you access to additional material and it really does help us make videos like this. If you've stayed with us this long, it only remains for me to say thanks for watching. Don't forget to subscribe to see more like this. Until next time, bye for now.